this is MarkMcDonald. I'm going to present to you my Pathfinder project from the Harvard Extension School Deep Learning class, spring 2019. Off-road robots have seen a wide variety of recent advancements. New applications include farming, military, search and rescue, security type of applications, where these robots can now traverse off-road environments. Are no longer limited to prescribed flat surfaces where they could roll over. What this project aims to do is to develop a deep learning model that's designed to help these autonomous off-road robots find a path that they can safely navigate. These are a few pictures from robots made by Boston Dynamics, which have an extremely impressive set of skills and extraordinary agility. We're going to use a Mac for our development. We're going to use an external GPU. The support libraries are basic ones that were used during class. No new special libraries are being used. And the model being used is a convolutional autoencoder, which will encode images and decode them as masks. The data set is large. It comes from the website listed here. It's 7 gigabytes. A toy data set is included with the project, but only just to get the project to compile and the model to train. It won't produce any real meaningful results. What's downloaded are 9 directories, 6 of which are training videos, 3 of which are testing videos. Each video is broken down into a series of frames so that the videos are basically a picture for each frame. The program relies on a Jupyter notebook called Master Pathfinder Notebook. It relies on 3 supporting scripts, one for data pre-processing, one for video support processing, and one for models. There are 2 additional support scripts used for creating special types of videos that I'll explain later. The user is going to be asked to create 2 directories to store the test and the training folders that are downloaded. The remaining directories will be auto-created by the program. You'll notice that in the example shown here, the downloaded folders include a series of frames, as mentioned, in a map file format. This format is essentially a data dictionary that includes a couple of arrays that we're particularly interested. One of them is the image array, and the other one is the mask. The image and the mask are overlaid on each other to create a superimposed image. The example here is from the manual mask that's created for the test data, but our model that we'll develop will create its own mask that will be overlaid on a test image to create a superimposed image. Those images will be stitched together into a video. This is an example of the perfect overlay that comes from the test data. These will be auto-created by the program so you can view what a perfect overlay will look like. Data generators are used in this program to overcome a small data set. We only have 600 images, so we used augmentation to extend this data set. There was a challenge here in that when an image is augmented, we also need to augment the mask in exactly the same way. This was overcome and solved. All the data generators for this project are included in the models.py script and can be reviewed there. This program also relies on what I call a description dictionary. Each model has a large number of adjustable parameters. So when we create the model, we save all of those parameters in a description dictionary. This will allow us to recreate the model later on or review what parameters go alongside of each model. This helps us create a video as well in later steps. This is a signature of the getModel function and the parameters that can be set. If none are set, the function will still work and all of the defaults tweaked a little bit. I found this model very sensitive, so be careful when making any changes to those. This is an example of the description object that holds all of the variables in it. Our model is very simple. It's defined in the models.py script. It's a basic simple autoencoder where it encodes the image and decodes into a mask. Here's a depiction of it just to get a visual overview of it. As I mentioned, the model was very sensitive to parameters. I found that dimension of 2400 was best. I found that color was best, oddly enough. ReLU was the best final activation. Sigmoid was usually suggested in cases like this, but ReLU worked astoundingly better. Regularization only caused problems. I found that between 30 and 40 epochs were best. Going past 50 just caused problems. I used a single dropout layer. Multiple dropouts didn't help. And only augmentation that did not rely on fill data worked best. So like zoom and a rotation with an associated zoom were the best augmentations to use. So the demonstration is a 7-step process. The first several steps are used just to set up the environment. Here in the first step, we are enabling Plaid ML as the backend. Plaid ML is the only Keras backend that supports an AMD processor, which Mac version Mojave will only allow. You can't use NVIDIA processors with Mac Mojave, so in order to use the eGPU, I was limited to Plaid ML. This option can be commented out without any problem, and it can be, with the toy data, this data set can be easily compiled and created with just CPU. The next steps ensure that we have a proper environment set. As I mentioned, the user is going to create a test and a train directory. Those directories need to be set in the script. The user also needs to create a top-level directory where all the auto-created directories will be created. And this can be the same location as where the test and train directories are. The fourth step will extract all of the respective data from the mat files and create images and masks that can be trained. The script step 4 will also extract all of the images from the test mat files and create a series of JPEGs that make up a test video. This is what the directory structure will look like after step 4. As I mentioned, the top 2 directories are created by the user. The bottom ones are auto-created. The user also needs to indicate which directory all of these things are in. The script will create an example video of each of the manually created overlays. These are stored in the train video directory as shown here. After that, we change the original mask data to be binary masks. The original data included 3 levels of data for the mask. We're going to narrow that down just to 2 levels of data, namely path or not path. Training requires us to use the getModel function that I mentioned. The default script includes the optimal settings. As I mentioned, running this with toy data won't have optimal results. I recommend downloading the full data set to see how this works best. The way the program is set up is you can extract a model from the models.py script using the getModel function. It'll give you a description object as well as a model object as a tuple. The training step in the script will take this tuple and train the model, as well as create a video. You can train multiple models sequentially, by simply appending a dictionary and model tuple to the model tuples list. TensorBoard is used to show the progress of training. I found this to be the best way to evaluate multiple models against each other. I found that models that ended up with a loss of around 0.5 had the best results. Not sure why, but that's generally how it worked. When the model is done training, the script will automatically create a results directory, or it'll create a folder in the results directory, which is auto-created, and it'll have a unique name for each training sequence. Inside of that folder, there's a data pickle file and a video that includes an overlay of the video that was created from that model. The data pickle file includes a description object and the trained model, so that you can retrieve that later and review the results. One of the support scripts that is included with the program, called Create Video from Pickle File, will ask you for a direct or a path to a pickle file, and it'll recreate a video for you based on the data pickle. And it's not necessary in order to create this initially. Actually, the support script is not necessary to create the initial video. The master script will create the video on its own. So after we've trained, we will get the video automatically created. I'm going to show an example of what that video looks like. In this case, these are 3 scenes stitched together. The first scene is harsh lighting conditions, and you can see that the model is trying to highlight the hay bales as non-navigable. Does a pretty good job of isolating the green blob that is navigable to non-trees and non-sky areas. This is a challenging environment. This last scene is much easier with a clear path. You can see that the blob is isolated to the path and the path only. As the robot navigates around the corner, the green blob latches on to area that it considers to be the path. This looks pretty good. I found this quite impressive, and I was pretty happy with that. I extended this a little bit to take a complete independent data or file video of a path from a mountain biking trip, actually, which has actually equally as impressive results. You can see that the green blob is mostly isolated to the path. Some of it in the tree area is isolated, and you'll notice sometimes it'll go outside of the path, but these are considered navigable areas. So you can see to the right, the skeet is highlighted as green, but that is navigable. The bushes and the trees are avoided for the most part, and it seems to be working quite impressively well, considering that this is a data set that the model never saw before. So thanks for your time. I hope this was interesting, maybe a little bit informative. Please feel free to leave a comment if you like, and I thank you for your time.